And let me say a few words. So first of all, good morning. Welcome everybody on our next course in the frames of Smarter for EU project. Today's course we have on very interesting topic. It's near zero energy buildings. So it's already fifth course which we have this year. And on behalf of Smarter for EU project, behalf of Association Energy Efficient Cities and Habitat for Humanity and other members of consortium of our project, let me say you welcome on this course. Wish you to find it very useful and interesting for you. Today, our trainer is Horia Petran. So he will introduce himself. I think it will be the best solution. So, and now I want to give the floor for official welcome words to Eva Mehraim-Aire. She is the leader of work package 5 in our project, in frame of which we are proposing these courses for our participants. So Eva, please.
Thank you very much, Vladimir. It's very nice to see you all this morning, and I'm pretty excited to see such a high numbers of participants. It's amazing that every time we have these courses, we keep the high numbers. So thank you very much, and your interest is really driving us forward. We are hopeful that there will be a few more courses also in the upcoming year. So this is really a great feedback. Please also do not hesitate to introduce yourselves if you would like to in the chat. And we are always very happy to hear about your feedback also by email after the courses if you feel like it. We would like to stay in touch because Smarter Finance for EU is a 2-year project which started in May. We are here to stay until at least 2025, but it's actually a kind of long-term initiative which started already in 2019. When we've launched our first Smarter project. Both of these projects been financed by the European Union, by the LIFE funding stream. And just very quickly to tell you what it is, what we are focusing on for those who are new here on these courses. Smarter is bringing together around 9 organizations in this second phase of Smarter, and these organizations are mostly experts on energy efficiency, green housing, but also finance experts, mainly green building councils. And our goal is to bring green certification closer to people, closer to developers, and also to create new projects for funding of green housing projects. So we are kind of the middle link between banks and the developers, and our organizations are trying to use the know-how in green housing to create conditions for the developers and banks to discuss about new projects, develop new funding streams for green buildings. We also believe that these kind of projects these are not solutions just for the rich. We would very much like to also include developers of housing for vulnerable families, for vulnerable groups. And that's why, as a part of the project, we try to find different solutions how to bring together public and private funding, and how to mix these different pots of money in the way which would suit individual projects. So going forward, as a follow-up of these courses, we are also hoping to have a few more individual conversations and start more individual relationships with developers of green housing projects for vulnerable families who would wish to get some more guidance from our side on the issue of funding of such projects. So this is enough about us. Now let me introduce the speaker of today's session. The speaker is Horia Petran. Horia has years of experience working in the field of nearly zero energy buildings, both as an expert, as a researcher, but also as a teacher. Currently, he works as a scientific researcher and also coordinator of the Building Knowledge Hub. But he has over 15 years of experience teaching at various technical universities in Bucharest. He's also a founding member of the Romanian Association of Energy Auditors and energy auditors for buildings. It's important. And he's also a president of the Cluster Association for Promotion of Buildings with Energy Consumption almost equal to zero nearly zero energy buildings. Yeah, hopefully I said the name of the association correctly. So Horia, the floor is yours. Please kick off today's course, and thanks again, everyone, for being here.
Thank you, Eva. Thank you, Volodymyr. I'm glad to be here with you. First of all, I'm Horia. And I don't know what to say more about me. The years of experience that Eva mentioned, in fact, are years of learning the energy performance of buildings. And it's the number of years that I've worked in the National Building Research Institute in URBAN-INCERC in Bucharest. I'm based in Bucharest. And like 10 years ago, I left my seat, my desktop in the office for some activities trying to discover the construction market. And that was the Build Up Skills initiative, when we built up the roadmap for the qualification of the workforce at that time for 2020. But from project to project, because the next one was Train to n-ZEB, we build up a strong relationship with the industry, and we funded the cluster, the Pro-nZEB cluster for promotion of nearly zero energy buildings. And in Train to n-ZEB, we developed the Building Knowledge Hub. I will show you in the last part of the training course the history of the Train to n-ZEB. We were 5 countries developing this concept, and one of the countries was Ukraine. So you have a Building Knowledge Hub in Kyiv. It was developed with the Municipal Energy Agency, I think, together with the Technical University of Civil Engineer and Architecture, something like this. Sorry, I'm not remembering the exact name of the university. And that was the story, the beginning of the story of nearly zero energy building, in fact, because nearly zero energy building, it's a concept and it's a standard. And I will tell you the story of it within the next 3 hours. And this was defined by a European directive starting 2010. It was a recast of a previous directive on energy performance of buildings. And since then, we know that this would have been the standard from at least 2019 and 2020. And now we know that we will face in 6 up to 8 years a new standard, which is zero emission buildings. So my opinion, my strong opinion, is that if we understand what the concept of nearly zero energy building is, we will easily make the transition towards zero emission buildings. But first of all, nearly zero energy building concept and standard are a very small part of the concept of sustainable building or green building. And I will start with putting into the context this part. It's a small part, but it's a very important part. I cannot imagine to have a green building that it's not energy efficient. And of course, a nearly zero energy building, which is a very high level of energy efficiency, can be a green building. So there are different concepts I will try to explain in the introduction. First of all, it's very difficult to make it interactive because it's online and because you are so many. Of course, I will ask you to keep your microphones turned off during the training course, but shift them on if you want to ask anything. So don't hesitate to interrupt me if you have any questions to clarify some detailed information. We will have some discussions after each part of the presentation if you have additional questions. If you don't want to ask them live, just put them in the chat in English or in Ukrainian, and then I will ask the interpreters to help me in understanding the question. And it is a very long course, very dense, but I will try to keep like 10 or 15 minutes at the end to have a discussion with you. So basically, this is the plan of today. The content of the course is structured, maybe not so coherent, but I will try to make it coherent in the story. First of all, by defining the nearly zero energy building concept in the green building or sustainable building context, which is larger. Then I will try to define the concept by the pillars that we defined, at least in Romania, but it's not the only country that is using a similar approach. And this is done by using the passive house pillars, the passive house concept. Even the Passive House Institute, I'm sure that you learn about the passive house. Even the Passive House Institute are evolving the passive house standard by embedding the renewables, which is in fact the nearly zero energy building definition. Then we will have a detailed journey through the building envelope, and this is one of the biggest part and one of the most important part of reaching the n-ZEB standard. And at the end, I will show you what we did, some of our projects. Maybe it will inspire you because I understood that most of you are from the municipalities, from the local administration. And it is not enough to have some provisions in a technical regulation or in the official journal. What's beyond the official journal, it's most important for the implementation of such a concept or such a standard in the market. So basically, this is the story that I will try to tell you. And first of all, let's see what is a sustainable building, what is a green building, because this training course is part of a long series of professional trainings that will help you to become a green building professional. And of course, everything starts with the emissions of CO2. Why? Because the CO2 emissions and the CO2 content is facilitating the greenhouse gas effect. And we are happy to live on a planet that it's offering a very narrow temperature difference and climate that facilitate our living. Without this, we will not live. So if we are trying to maintain this, we are not saving the planet, we are saving ourselves. And that being said, this CO2 is making a protective atmosphere that is hitting us. And by hitting the environment, rising the level of temperature on the surface, it's going to change the way that the nature is behaving, to change the climate. And in this context, we faced since the 50s, when somewhere in a laboratory in Hawaii, the continuous level of CO2 is measured. We faced a very abrupt rise in the CO2 level. And this is following a period where punctual measurements were made by different techniques. And we can easily see the rapid increase in the last years. And coincidence or not, an overlapping with the period of industrialization. So basically, what I can see here, it's the level of CO2 in the atmospheric air, which on one side, it's putting a pressure on the indoor air, because we will speak the whole training course about buildings. It is putting a pressure, because if we want to have comfort inside, we have to ensure the quality of air inside. And usually we are using outside air. So the more the outside air is polluted, the less we can dilute and we can ensure the indoor air quality. On the other side, we are taking something from the nature in order to build our buildings, our built environment, and we give less back. And this is the story of sustainable buildings. And we are speaking about sustainability. We are speaking about restorative sustainability, regenerative sustainability, in an evolution of understanding about what we are dealing with the nature, because if we are fighting with the nature, we will not win. The nature will fight back, and this is what we are facing now. So we started from the business as usual, the industrialization, and then we try to understand what we are doing, and we try to reduce the impact, and then we speak about green buildings, for example. And this is the context of sustainability, because this is the next step. It's to limit the damage caused by us to the nature. But then there are concepts that are developing now. And of course, if we take some steps back and look in the back, we can see that it's a lot that we have taken from the nature. So we try now to restore the capability of socio-economic and ecological system to a healthy state, and more to give more back that we are taking in the regenerative sustainability concept. And of course, just to complicate more, we are speaking about biophilic design. And this is a design that improves the comfort and the health through a connection with the nature. And even if there are different concepts, biophilic design, energy performance design, sustainable design, they have many points in common. And the centric point, I think, it's the people occupying the building. We are not building the building for the sake of the building, or to put a label with the name of the architect. We are building the building to ensure comfort and health of the occupants. And connecting with the nature is one of the best ways to ensure this comfort and to ensure this link with the environment. So we are speaking about buildings, we need that, and we are occupying like 85 to 90% of our time these buildings, either at home, either in the workspace at the office, in a bar, restaurant, drinking something with our peers, or in other indoor locations. So this is important for us and, of course, important for the buildings. But first, it's about us. And if we are putting into context the energy need or demand to ensure the comfort, we are starting from the occupants. And this is a simple balance, and it's a basic balance, because we will use that in every sentence when, or every situation when we are speaking about the energy performance of a building, which of course is part of the sustainability of the building. So in order to maintain the comfort, we need to cover some heat losses, or to balance some heat loads in winter and in summer. And these losses are through the building envelope. It is called a transmission loss. And we have to heat or to cool the air that we are breathing. And this is for the hygienic comfort. And then we have the gains, the solar gains and the internal gains, which are more or less free gains that are taking into account in the energy balance. And I will get back with that in some mathematics formulas, because we have to understand how to put all together in an energy balance in order to say something about the energy performance of the building. But what is very interesting in this diagram, it's the blue arrow on the top. Because what we are doing with the building, we are also generating or eliminating or transferring some heat to the environment. And in this context, we are seldomly speaking about isolated buildings. One building placed in the nowhere. We are putting buildings together in clusters, in districts and in cities. And here something special is happening, especially in the summer, where we have the thermal urban island effect, with an increase of, I don't know, 2, 3, up to 15 or even more degrees more than outside the cities. And it's one perspective to speak about the energy performance of a building from the perspective of that building, but also to speak about the energy performance of a cluster of buildings at district level or at city level. So with this introduction, I will jump to the sustainable or to the green building. And this is defined in terms of the well-known definition of sustainability. We are building our indoor environment because we need it, and we take something from the nature. So we have to respond to our current needs, but we have to think that we should not take something for the future generation needs in order to answer to our needs. So this is the perspective in which we are speaking about sustainable building. We are not breaking or compromising the ability of future generation to meet their own needs, to do the same thing that we are doing now, and allowing them to do that. And in this context, ideally, the boundaries would be set from the extraction of raw materials, including resources, fuels, until the end of the product's lifetime. And we have resources that we're extracting. We are transforming resources in materials, materials in products, products in systems, and we assemble the systems on site in order to have the building. So we should include in the life cycle assessment the energy from manufacturing, from transport, the energy to manufacture capital equipment, the energy demand in the factory, for example, the energy to heat or to light the factory, the maintenance, the disposals, and everything else. So we are speaking about the cradle to grave that is covering the whole life cycle, or the cradle to gate, which includes all energy in the primary form, in resources form, until the product leaves the factory, or cradle to site, which includes all the energy consumed until the product has reached the point of use. In our case, the buildings. In all this life cycle, of course, we are speaking about circularity, about circular economy. And if we are coming to the decision to demolish the building, at the end, we have to seek first to recycle what is to be recycled, to reuse what is to be reused, and then to minimize the waste. So what we dispose should be minimum. And on the other side, now we can see with yellow on the bottom, the use phase, the occupancy and maintenance phase of a building, which is the longest period of a building until now, with the biggest impact on resources. And this is the context where concepts like zero emission buildings, zero energy buildings, or nearly zero energy buildings, or passive house, or active house, or other concepts are limited on the occupancy and maintenance phase of a building lifetime. In order to say that a building is green or is sustainable, we have several standards. The well-known are the American one, LEED, or the British one, BREEAM, or the German one, DGNB, or others. In Spain, for example, there is a mixture of standards. They have their own standards. And in Romania, we have also a simplified one, which is called green building, and it's used for green homes, sorry. And it's used for green mortgage. And if we take one of the standards of the certification standard for green buildings, just a random example, BREEAM, we can see that in order to certify, we have to follow a rating. And it's like a benchmark rating, taking into account some key criteria, like management, health and well-being, energy efficiency, transport, water, waste, pollution, land use, and ecology, materials, and innovation. And we will have a global rate based on individual rate for each of these criteria. And if we are going towards nearly zero energy building, it's about two of these criteria that are important. First of all, the comfort and the health of the occupants, taking into account the visual comfort, the acoustic comfort, daylight, lighting, acoustics, the quality of indoor air, and thermal comfort. And then it's energy efficiency, including the CO2 emissions that are generated from the energy demand, from the energy supply to cover the energy demand. So this is the boundary where we are speaking about concepts like nearly zero energy buildings, or passive house, or active house, or other concepts that are focused on the use phase of a building. And I just took two apparent antagonic concepts, which are passive house and active house, because you can see passive and active are quite opposite. But from the perspective of defining the concept, of course, the standards are quite different. They are considering different criteria and different values of this criteria. But from the point of view of the concept, we are speaking about ensuring the comfort with a very low energy demand, which is the passive house. And we are speaking about indoor environment, the environment itself outside, the energy efficiency as concept to ensure the health and well-being of the occupants, which is the active house. And if we are looking on the two pictures that are used for these different standards, that are voluntary standards developed by the market, for the marketing, we don't see any difference. We see kids which are vulnerable, playing in a comfortable and healthy building. And this is the starting point of defining the nearly zero energy building. And this is a very nice diagram developed by my colleague Sonia in her PhD thesis, starting to approach n-ZEB by sustainability. And yeah, it's about connecting to natural environments, so some pieces of biophilic design, natural cross ventilation and mechanical ventilation with heat recovery, balancing natural and lighting with solar protection approach, accessibility, water management, and use of renewable energy on site. And these are some pieces of the puzzle that are forming the global image of nearly zero energy building. And finally, let's see what is the official definition. The official definition is coming from 2010 from the recast EPBD. And in the member states, it was transposed in the more or less declared period from transposing. In Romania, for example, it was transposed 3 years after the publication in the official journal of the directive. So we knew about nearly zero energy building from 10 years ago. First of all, n-ZEB, it's nearly zero energy building. B is from building. So first of all, it's a building. It's a building with a very high energy performance. And the very high energy performance is determined in accordance with the Annex 1 of the EPBD, of the Energy Performance of Buildings Directive. That means that we will have a demand of energy which is very low or nearly zero. That means that we have a very insulated building with a very high performance envelope and with very high efficiency of the system supplying the energy demand. The next step is to cover this demand in a very significant extent by energy from renewable sources, including energy from renewable sources produced on-site or nearby. This is the general definition that should apply to every member state. And here are some comments that I should make. In red, you have the energy. In green, you have the green energy that should cover the red one. In sparkling red, it's the word including. And it was done by this manner in the general definition, and it was accepted only like this because of the principle of subsidiarity. Because the directive is a European law that is not applying per se. It is applied by transposing the text into the national legislation. And some of the member states use green energy, which is not produced on-site or nearby. So the word included was not to limit to on-site or nearby. And then in some member states, and I'm very ashamed to say that also in Romania, they copy-pasted the translation of the directive. And they put also including. And this is why from 6 months we have the definition of nearly zero energy building with this including, and with the primary energy factor include from the national electricity system, including also something that is not due to the building. It's not related to the building. It's a 25% green energy included in the energy supply in the national system. And of course, the idea and the spirit of the directive is to put renewable systems, renewable energy systems on the building or on the property that is related to the building. Let's translate this text, which is vague but precise in the same thing, in the same time. It's about enforcing the national requirements, the minimum energy performance requirements, going as much as possible towards nearly zero, towards zero. And this is a matter of costs. This is a matter of filtering the energy performance based on the cost optimality calculation. And this is done by each country at national level, taking into account the building sector, the traditions in the construction sector, the economy, the power to buy things, everything. So this is the first step. First of all, reduce the demand, and then the reduced demand cover as much as you can from renewable energy produced from renewable sources on site or nearby. And what is here to be mentioned is that beside this general definition, in order to say about a building that is nearly zero energy building or not, you have to set up some criteria, some requirements. And there are 3 key performance indicators that I took into account in the assessment of the n-ZEB standard. This is total primary energy, including renewable and non-renewable, the renewable share, the cover from the total primary energy that is supplied from renewables, and the CO2 emissions. In Romania, in the first transposition of the directive, the very significant extent of energy from renewable, it was set in the legislation at 10%. This was in 2013. And then in 2020, we modified to 30%. So in Romania, we have one of the indicators set for all the buildings at 30%. The other ones are set on building type, building category, if it's an office, if it's a residential, if it's a hospital or a school or a commercial building. And by 5 climatic zones that are set up for winter, for design the heating systems. So basically, this image showed the definition, showed the steps that we have to take. First, reduce the energy demand, then cover the reduced energy demand by renewables, and then having the standard defined by the 3 key performance indicators. So I will stop here just to take some questions and then maybe to have short break of 10 minutes. Do you have any questions? Are you still there?
Yes, everybody's here.
Чи міг би я коротенький, може, коментар і запитання водночас?
I assume that it's about a question in the chat. How do you calculate CO2 emissions? First of all, the CO2 emissions that are accounted in the n-ZEB standard are related to the energy consumed in the building over 1 year. So if we know the resources that are used to heat, to cool, to ventilate, to ensure the lighting, and to ensure the domestic hot water in a building, then we can multiply the value of the energy demand for each energy carrier with the transformation factor that is set up at national level in all member states. We have a table in the Romanian methodology, for example. For gas, we have gas from the network. We have a transformation factor from energy, kilowatt hour per square meters and year, to CO2 emissions, kilogram CO2 equivalent per square meter and year. And we have transformation factors for coal, for wood, for energy from the system, for liquid fuel, for all the energy carriers that we can find on the market. So if we know the energy demand, which is the tricky thing for each energy carrier, then it's a very simple mathematical calculation to do that. Good. If there are no further questions for this introductory part, I will propose you to have a less than 10 minutes break. 5 minutes to 11. It's okay to get back?
Yes, 10 minutes will be good.
Good. Thank you very much. See you then.
Yes, please do not switch off your Zoom. And see you in 10 minutes. For participants who have joined last minute, I want to inform we have short break, and we will continue in 5 minutes.
we're back in business. After the short break.
Yes, we can continue.
Good. So there is more about the n-ZEB besides the definition. Now, as we accustomed with the definition, we know the standard because we know the key performance indicators. These have to be checked at the end in the commissioning of the building when we are starting the occupational phase by the energy performance certificate. This is done in many countries. This is done in Romania. So we know where to go, but how to do it. And this is the first question. And it makes sense to start from the first phase of the two, which is having a nearly zero or very low amount of energy required. And the best way to do it is starting from the passive house experience. And first of all, what is passive? Let's take the very simple example of preparing coffee. We have to supply energy to prepare the coffee, and we can do it in a filter machine or put it in a very well insulated container, which is the thermos. And the difference is that in the first case, we have to supply a lot of energy. In the thermos, we supply the energy to produce the coffee, and then we maintain it for a very long time at the desired temperature. So it's about the difference that a high-quality envelope is making in this concept. And it's a very simple example and very useful example to go to the building. And starting with the inventory of the 5 pillars of a passive house. Passive house was a concept developed by one German guy and one Swedish guy in the 90s with a purpose to define a standard that is offering comfort in the Central European climate without any heating system. So that was the purpose, the design scope. And the 5 pillars of the passive house are very simple. First, a continuous layer of very good insulation for the opaque part. The second one is high performance windows and doors. Nowadays, the standard for this is the triple glazing with double OE and an argon or xenon or krypton gas inside. Then it's avoiding the thermal bridges to have the continuous layer of insulation even when we have connections, joints between building components. To have an airtight envelope. Airtightness is one of the most important key performance indicators of a passive house, and it's part of the standard. This is measurable. We will speak about in some minutes. And then the 5th one is to ensure fresh air where it's needed, when it's needed, with a mechanical ventilation system that reduces the heating demand from the air for the ventilation with heat recovery in a passive way. And then it's about the details. In red, you have the key indicators that are forming the passive house standard. This is something that we miss, like the heating demand or the cooling demand, we miss in our definition of n-ZEB. We do not have this partial performance indicator. It's not about reaching the standard when we are speaking of the passive house. Passive house is a voluntary standard. It's well spread over the globe, but it's voluntary. n-ZEB, it's a mandatory standard in the member states in European Union. But it's worth to have a discussion about trying to reach the standard as a good way to easily reach the n-ZEB levels. So based on this, we have the 5 pillars of the passive house that we could include in the n-ZEB definition. Is the high performance building insulation, high performance windows and doors, air tightness of the building envelope, minimized thermal bridges and mechanical ventilation with heat recovery. If we put another one, which is somehow hidden in the concept, and we call it optimum building shape and solar gains optimization, which is a matter of configuration, and it's very useful when we have to design a new building. Then we have the first set that is ensuring a low energy demand. And if we put some partial key performance indicators in each of these pillars, it will pave the way for the n-ZEB standard. For example, in the building shape, we have the ratio of building envelope divided by the volume. In the solar gains optimization, we play with values of solar transmittances and shadings. In the building insulation, we are imposing maximum U values, maximum transmittances. On windows, we have maximum transmittances and solar transmittances. In the air tightness of the building envelope, we have the N50. The air changes per hour at 50 pascals. Minimized thermal bridges, we have the maximum C values. Mechanical ventilation with heat recovery, we have the SPF value, the power absorbed by the ventilators to vehiculate 1 cubic meter per hour of air, and also the efficiency of ventilation. So if we understand this and if we set up this in our regulation, then it will be a good way to go to the standard. First of all, let's see how we can calculate the energy performance. First of all, this is the energy needed, the energy demand at the occupied spaces. This is the indicator defined in the passive house standard with a value of 15 kilowatt hour per square meters and year. And this is calculated to cover the transmission heat losses, to cover the heating of the air for the ventilation, and it's helped by the gains. And what we need to know is the forms of thermal energy exchange in a building, which are conduction, convection, and radiation. Usually they are combined. For example, in a window system, we have all 3 of them. We have conduction in the solid glass and in the solid material of the frame. We have convection in air spaces or gas spaces, and we have radiation between various surfaces, for example, between 2 glazing surfaces. Usually we have 2 or all 3 combined in the energy balance. The energy balance starting from the occupant is starting from the useful energy by covering the heat losses through transmission and through ventilation, and getting some help from the solar gains and internal gains. And the result is QH, which is the remaining heat demand that should be covered by systems. And in order to cover this by systems, we have some inefficiencies, some losses in the connection, in the emission system, in the distribution system, in the storage, if any, and in the generation system. And then we come up to the final energy boundary, which is the building boundary. It's the energy counter. Then we calculate the final energy. But this is not enough because we need resources, and the type of energy, the energy vector, it's very important in terms of the emissions that we will generate with the final energy. So we are going beyond to the resources by taking into account the primary energy. And then, of course, we divide the primary energy in non-renewable that is supplied by fossil fuels, or renewable that is supplied by energy that are using renewable resources. So this is what we have to calculate. It's a very simple schematic balance. We have to set the boundaries, and we have to take into account what are the services that are included in the energy performance. In the Annex 1 in the EPBD, there are some examples. Some of the services are mandatory, some of them are not. So in some member states, you will have different services that are included in the energy demand. In Romania, we include all the 5, which are the heating, the cooling, the domestic hot water, the ventilation, and lighting. So if we have the energy demand at useful energy level and at finally energy level, on different energy carriers, we can calculate the primary energy for these 5 services. We can use a software. This is only one example, it's not the only one. This is the tool that is used to design the passive houses. It's the PHPP, Passive House Package, Planning Package. What is important here is that we have on the left the losses for ventilation and transmission through opaque part and through transparent envelope, which are the windows. And on the right, we have the gains, the solar gains and the internal gains. The difference between them, it's the remaining heating demand. And this is what is compared with 15 kilowatt-hour per square meter in the passive house standard. And of course, we can use whatever software tool we found on our market, and it's required or validated through our national regulation. But what is important, if you look on the balance of windows, you can see easily that the gains from windows, it's bigger than the losses from windows for this case. And this is one important thing, because it's not only transmission losses or ventilation losses that are important, but also the gains, the solar gains that are covering part of the losses. And having a remaining heating demand very low is depending on the losses, but also on the gains. And let's have a journey through all the pillars that we mentioned. First of all, building shape and solar gains. We have the building shape. We have on the right an indicator, which is the building envelope area divided by the conditioned heated volume. And we have a benchmark. Depending on the shape of the building, we will have a good or a bad start in the energy performance journey towards n-ZEB. So it is about the shape of the building. Of course, the optimal shape is the sphere, but it's very hard to imagine a building in the form of a sphere hanging by the sky. So the next one is the cube, and then as much as we play with the shapes, with the volumes, we will have a bigger ratio building envelope area divided by the volume. So we have a benchmark of this indicator, 0.6 square meter per cubic meters of building. But on the other side, it's about the urban context. Is the connections between buildings, because if we want to build a building that will be a passive house in a dense urban area with very high buildings, we will have a problem of using the solar gains. And also it's about the corridors that are between buildings and that can intensify the circulation of air. We can have intensified winds in some areas, and this will affect also the heat losses and consequently the energy performance of a building. In terms of summer comfort, it's very important to balance the need to have high gains in winter and to maintain a lower temperature in summer. Because in summer we have solar gains, which are in fact in the summer solar loads, because they will increase the need to cool the building, and internal heat gains. And the first way to solve this problem is to have the night ventilation. So it's important to design the building in order to allow for cross ventilation, in order to use as a passive technique to cool the building. And also the thermal protection, the building envelope insulation is helping, but also if we leave the heat to enter the house, to enter the building, it might be stored in the massivity, in the thermal capacity of internal elements, and then it will be very delicate to release to the building environment, because we have a very good thermal protection of the building envelope. So it's also a matter of use of a building. And this is very simple by passive techniques. Night ventilation to cool the building if we have enough temperature difference, shading to reduce the solar load, efficiency to reduce the internal heat gains, and of course, thermal protection, who is helping in this situation. The second one is high-performance building insulation. We have here a very schematic comparison of the German standards and the passive house standard. In the German standard, if we look back like 15, 20 years ago, we would have seen a big difference between the key performance indicators compared to the passive house standard. Now the differences are getting lower and lower. The passive house standard remain unchanged. On the right, you can see the values that are recommended for the Central and East European climate. Of course, in Ukraine, it could be lower than that, the maximum transmittances that are recommended in the slide. On the left hand, we can see the values from the, I think, older, it's 2009, German regulation. Now, instead of 0.28 watt per square meters and Kelvin, it's 0.23. And for Romania, from a couple of months, we have 0.25 for new buildings at n-ZEB standard. Then it's high performance windows and doors. And this is important because a window in a conventional building, it has a very high transmittance. That means that in winter, we have a very low internal surface temperature on the window. And this is causing discomfort. This may cause also mold growth or condensation even. And usually the tradition is to put a radiator to compensate this cold temperature. And first of all, so it's a matter of comfort. And then it's a matter of heating load. So we have to put a lot of equipment in order to maintain the comfort inside. In a passive house, we have a very warm surface, even in the windows. And we have a very good thermal comfort. In terms of indoor air temperature, in terms of radiation temperature, in terms of stratification or differential temperature in a space. And what is very important is that if we reduce enough the heating loads, around 10 watt per square meter, then we can use the ventilation air to heat the building. And the second thing that is very important is that the window, it's using, it's one of the entrance doors, one of the entrances for the sun, for the free heat that we will include in the balance. So we have the technology on the market, and it's the market is growing. Now, in Romania, we have all the technology possible, even produced in Romania, or with very short supply durations in the warehouses. We will see when we will detail this principle in the building envelope description, that the performance of a window is important in terms of transmittance, thermal transmittance and solar transmittance, and also where we install the window. And on the left side, you can see a technology to install the window in the future insulation layer in line with the continuous insulation layer. The air tightness of the building envelope. If we have a gap, a small gap in a structure that is presented in the image, which is a structure of a roof, a gap of 1 millimeter, in one day, we will have 360 grams of water passing there, vapors, that could condensate if it's a cold surface and can accumulate. And if instead we put an airtight barrier, a membrane, we can have only 1 gram of water per day and square meter. And this is reduced the effort to repair the structure. And this is one of the most important reasons to have an airtight envelope. And first of all, we should have a difference between air tightness and wind resistance. The air tightness, it's important to prevent the airflow from outside towards inside or from inside towards outside. If the air is passing the building envelope from outside to inside in the winter, we will have cold drafts, cold surfaces, so thermal bridges, and the risk of mold development and condensations increase. If the air, which is warm air with a water content, vapor content, is passing through the building envelope from inside to outside, we will have the risk of condensation and deteriorating, even destroying the building envelope component. The wind resistance, it's about not letting the outside air entering the insulation material, because we will have, as in the first case of air tightness, we will have depreciation of the insulation effect of the insulation material. But here we have a traditional question. Shouldn't be necessary for a building to breathe through the walls? It's not about breathing. It's about the capacity of the building fabric, of the building material, to absorb and to release the absorbed quantity of moisture in order to allow the humidity transfer. So it's not about breathing, it's about transpiration more, because accumulation of humidity can be a problem. So we have to ensure that the materials and the structures that we are designing are fit for the purpose, because otherwise we will have the case on the image on the right, which is a very severe mold development. So no, we cannot, we shouldn't breathe through the building walls, as we shouldn't breathe through the skin as humans. The quantity of oxygen that we are taking through the skin, it's not sufficient to help us living. We have a respiratory system. In the building, this is the mechanical ventilation with heat recovery. So it is very important to have a continuous airtight layer. And we have the pencil rule, the golden rule for that. We will use that also for the continuity of thermal insulation layer. And what is important is to take care of details. If we are speaking about airtightness of a building envelope, this is a concept. And to understand this concept, we take care of three things. Airtightness of the surfaces, airtightness of the connections, and airtightness of the penetrations. When we say connections, we refer to different building components and, of course, windows and doors and opaque part, walls, for example, or roof. The airtight areas that are considered conventionally airtight in a durable way are the internal plaster, the sum of the wooden composite boards, the concrete, and specialized foils or membranes. Usually, we are using the vapor barrier or vapor retardant as airtight layer in some of the structures that we are building. The airtightness performance is a measurable performance. We use the standard, the European standard and international standard EN ISO 9972, which is the blower door test standard. The blower door, it's an equipment with a flexible frame, with a flexible sheeting and a fan. Pressurizing or depressurizing a building, so inducing a pressure of standardized 50 pascals between indoor and outdoor, measuring the airflow and measuring the pressure difference. And in the technical regulation at national level, if we want to take into account airtightness of building envelope, we should at least recommend the blower door test and fix some thresholds. For example, for the passive house, the maximum value allowed is 0.6 and 50, number of changes per hour at 50 pascals. For NRFIT standard, which is renovation at passive house standard, we have 1. In our building regulation in Romania, we have 1 air changes per hour at 50 pascals for all the new buildings, which is the n-ZEB standard. The fifth pillar of n-ZEB is minimized thermal bridges. What is a thermal bridges? Thermal bridge is an area of the building construction which has a significantly higher heat transfer rate than the surrounding areas, the surrounding materials. We can have in a change of materials, in change of thickness, geometry of the building element. Basically, we are calculating the transmittance for the infinite walls or building components. And then when we couple 2 walls or 2 components, we will have at least a geometric thermal bridge. Why are these thermal bridges so important? Because they increase the heat loss, so they will reduce the energy performance at the end. They will lower the internal surface temperature in winter, so we will increase the condensation risk or the risk of formation of mold or fungus. They will affect the discomfort by having cold spots or cold areas or cold drafts if it's about airtightness. Increased dust buildup on surfaces because of an increased thermal exchange. and possible destruction of building components, cracks, and efflorescences. How we will avoid the thermal breaches? By the golden rule, the pencil rule. We should avoid the weak points. If we can maintain the pencil on the paper while drawing up on a plan or on an elevation the contour of the boundary of the building envelope, it's okay. If we take off the pencil from the paper, then it's clear that we have a weak point. We will have a thermal breach over there. Usually we are calculating in the design process the transmittance through components and the linear transmittance C value through the thermal breaches. And the sixth one is mechanical ventilation with heat recovery. This can be done in the centralized way with a central unit, as you can see on the left, and with the local unit, as you can see on the top in the picture. It's about the fact that ventilating as traditionally we do through the windows is not sufficient to have a hygienic comfort in all the times. And on top, it's about the pollutants, it's about the smells, it's about the clean air, the filtered air, and it's about having the exact amount of fresh air in all the supply rooms and to extract the pollutants and the smells from the kitchen, from the sanitary groups in an efficient way. If we can put together the two flow rates, the supply air rate and extracted air rate in one passive exchanger, heat exchanger, then we can recover the heat. And the basic principle is to cover all the surfaces, all the volumes of a building, dividing the building in supply zone, extract zone, and in between the air transfer zone. This is the cross ventilation principle. It's the most economic way to do it. Is to have exactly the same as much as possible flow rates for supply and for extract. And if we can put all these flow rates in a heat exchanger, we can recover up to 90% of the heat that is included in the extract air. Assuming that we have a building that is heated in the winter at comfort temperature of 20 degrees, the quantity of heat that is embedded in the extract air that will be exhausted through the outdoor environment is recovered by preheating the fresh air, the outdoor air, up to 16-17 degrees. That means that we will not, in this example, we will not heat the air from 0 degrees to 20 degrees. We will heat from 70 degrees to 3 degrees. And this is the energy efficiency, the energy saving that in terms of energy, cost effectiveness, will cover part of the initial investment in such an equipment, in such a system. So we saw the first 6 principles, and we need to add more pillars to the n-ZEB to complete the whole image. And this is about significant renewable energy sources share. It's about minimize CO2 emission, but if we have obtained a low energy demand, we will obtain minimum CO2 emission. If we look on the energy vectors, on the energy agents that we use in to supply the energy. And this is about resources. And last but not least, it's about cost efficiencies or cost feasibility. We can do whatever we want. We can build spaceships, but if we have the money. So not all the investments, initial investments, and all the cost can be recovered through the energy savings that we are doing. And about the cost efficiency, this is a very simple comparison. I would say rather simplistic, but very suggestive, between a passive house and a usual practice one. It's a difference of 90%. We can reduce like 10 times. We have the potential to reduce like 10 times the energy demand. And of course, also the CO2 emissions. So these two are related. And it's a matter of shifting from thinking in terms of initial investment towards global cost over the lifetime of the building or the occupational phase of the building. And this is usually standardized over one generation, which is 30 years. For some buildings, in the regulation for cost optimal that was issued by the European Commission, it's 20 years, for example, for office buildings. For residential, it is considered 30 years. And it's about putting together all the costs from the investment phase and for the occupational and maintenance period of a building. So it's a balance between the initial investment cost and operating cost, and not always the most cheap investment is the best one, and not always the highest investment are automatically bringing the best possible. So it's about a paradigm shift of thinking in terms of global costs instead of initial costs. And then it's about using the renewable energy sources to supply the low energy demand that is required. And we have the biomass, we have the solar and wind energy, we have the geothermal energy, the water energy. We can use systems that are available on the market. And of course, the most effective is the sun. And we have now technology that allow us not to limit to the horizontal surface. We can put also on transparent surfaces of the building envelope solar panels or solar collectors. We have a growing market on that, and the regulation is taking the pace with that, fortunately. About the minimized CO2 emission, of course, is the starting point. And yeah, I didn't have a recent collection of the value, but as you can see, the CO2 emission is still growing at the Hawaii laboratory in Mauna Loa. And it's growing and it's growing. And of course, the standards of ventilation take into account these growing values. If we are going into a dense populating or a polluted area, values could be much higher. And this is not something new. It's about the 80s with the solar buildings. It's about the 90s with the free little fuel building. It's about the low carbon footprints in UK and also the zero emission buildings in Norway and in other countries. And it's about sustainability in buildings that is the new trend. How to have the minimum impact on the environment. And this is about the carbon footprint on the life cycle of the building. In Romania, we have a minimum 30% of energy demand supplied from renewable energy sources. That is contributing very much to the minimized CO2 emissions. And what is to be mentioned? I mentioned in the start, the n-ZEB standard, it's a transition standard towards zero emission buildings. We will have a new directive at the beginning of next year. That's for sure. It's in the final phase of a trialogue between the Council and the European Parliament. And if we put all this together in the concept, we have 9 pillars. If for each pillar we have key performance indicators, we will have a very good concept. We will have a very good map to achieve the n-ZEB standard. So this is the n-ZEB standard, and it's only a matter of using the existing technology with the layer of energy balance in a building. If we put those layers together, the energy balance and the technology balance, we can solve the n-ZEB puzzle. If we take care of insulation, of internal massivity, of thermal inertia in the building, of the daylighting, using daylighting together with the artificial light, the solar control, using selecting glazing and highly performance windows, efficient HVAC systems, heating, ventilation, air conditioning, using efficient electric appliances. Maybe electric appliances, at least in Romania, are helping in the winter because they are considered internal gains, not in the energy performance of the buildings, but for sure in summer they will generate the need for cooling. The building control automation, the building management systems are very important, and then there is a great variety of renewable sources that can be used with existing technology to supply energy in a building. The energy performance certificate is very important. It is mandatory in all states, and it's, I think, in all states, the tool to check the energy performance of a building at n-ZEB standard. In Romania, from 2016, we have the obligation to have primary energy in the classification, but only this year, after 7 years, we comply with this legal requirement because we published a revised methodology for calculating the energy performance of a building. And we have a new classification also with a new CO2 class and scheme. And we have all the key performance indicators to check with the mandatory thresholds that are defined in the same methodology, which is the total primary energy, the CO2 emission as maximum values, and renewable share with a minimum 30% as per Romanian regulation. So this was the second part of getting through the principles, the pillars that are defining the n-ZEB concept. And if there are no questions, the chat is empty. Hallelujah. I will continue for 10 or 15 minutes, and then we will have a short break with detailing a bit what is related from those pillars that we saw for the building envelope. How to define the building envelope in order to reach the n-ZEB standard. So it's additional perspective in terms of building physics, but also a detailed perspective in order to see what are the requirements for a building envelope. And I think the most important thing is to understand what are the functions of the building envelope. What is the scope of the building envelope? So the goals of the building envelope is to protect from the bulk water, to protect from the wind, to ensure good insulation and air tightness performance, to control the vapor transmittance, the hygrothermal and mass transfer, and to prevent overheating. Because the building envelope should contribute in a very significant extent to the healthy and comfortable environment for the occupants. And if we speak about comfort, it's not only thermal comfort that it's required. It's also the indoor air quality, and for that we have ventilation. It's the sound protection, and for that we have to check the thermal insulation and all the materials of the acoustic properties. And of course, if we are speaking about systems, for example, to solve the indoor air quality problem, we use ventilators that are producing vibrations, and we have to ensure that a certain level of sound protection is ensured in order to have a comfortable acoustic environment. And last but not least, it's about visual comfort. This is about light and colors and properties of the light, but it's also impacting on energy performance if we do not balance very well the natural light with the artificial light, which is the lighting system. So this is more complex than energy performance and energy efficiency. And it's very important to define the building envelope, because when we are doing an energy balance of the building, we are writing the energy balance and the mathematical formulas on the specific boundary that we are defining. And this boundary is the thermal envelope. This is the skin of the building. It's the physical barrier between the conditioned heating and cooling internal space and the exterior of the building. So when we are defining this thermal envelope, we have to understand what is the importance of the details that we will have to solve later, at least in what concerns thermal bridges and air tightness. The requirements for the thermal envelope, here I will put the safety first. And we have the fire safety, of course, the security, the damage-free, the quality of construction, the thermal bridges that should be minimized, the air tightness, and the vapor control property of the building envelope, of the structure. Is the control of water vapor diffusion in order to reduce the risk of water accumulation in the building structure and to reduce the risk of condensation or mold development in the building fabric or at the indoor surfaces. There is a wide range of material, insulation materials and systems available on the market, but doesn't mean that each of them is adequate or proper for every application. In terms of building envelope, we can see the natural behavior of a little bird, improving the comfort, minimizing the metabolic loss in order to face very cold environment. But also we can see an adaptable or adaptive envelope, which is thicker. The feather envelope, it's getting thicker in order to ensure the thermal protection when it's very, very cold outside. So if we are speaking about a good insulation, we are speaking about thickness and about the property of the material. In this case, the most relevant is the conductivity, the thermal conductivity, which is usually written with lambda, which is the rate at which the heat is transferred by conduction through a unit cross-sectional area of a material when a temperature gradient exists perpendicular to this area. And there are many classes of materials and different materials that have different thermal conductivities. And in a standardized way, we can accept as a material has insulation properties if there is a conductivity less than 0.1 watt per meter and Kelvin. The golden rule or the pencil rule is used to ensure the continuity of the insulation layer. The scope is to have an unbroken thermal envelope. About the properties in the heat transfer, we have thermal conductivity, lambda, which is a property of material, and thermal resistance, or the opposite, which is the thermal transmittance, the U value, which is a property, or both are properties of a component. These are the measure of a material, of a component's ability to resist heat transfer. So, in terms of calculation, I just mentioned that we are using for the heat transmission, the calculation through components, and we are using the U values through joints and details. We are using the psi values, and through breakthroughs, penetrations, we are using the point thermal transmittance heat. This is the usual way of calculating. It's a simplified way. The basic method uses the steady state heat transfer. The U value and the R value, the resistance, are values that are defined only in steady state transmission. For multi-layers components, we are calculating the U values, the transmittance values, or the thermal resistance values, adding the resistance of each layer in a multi-stratification component. In terms of materials, the materials, of course, are classified considering their thermal conductivity. And with a given thermal resistance that has to be achieved, we can calculate the thickness of the material that is needed to achieve this transmittance. Or, for a given thickness, we can calculate the thermal resistance. The better the material is, the higher the thermal resistance is. And the U value, it's the transmittance that is the opposite of the thermal resistance. And of course, on top until now is the aerogel. Then we have the phenolic foams, we have the polystyrenes, we have the cellulose, the wood fiber, the glass wool, the rock wool, basaltic rock wool, the sheep's wool, and then we have the classical materials: timber, brick, glass, concrete blocks, reinforced concrete, and the metals that we couldn't see very well in this graph. So there are different insulation materials that we can see on the market. Natural materials, already mentioned wood fiber and cellulose, and also some materials that are either from artificial processes or from oil, like the polystyrene and different foams are. We mentioned about the aerogel, which is putting the air in small places, encapsulating air, because the air is in theory the best insulating material if it's steady, if it's not moving, because if it's moving, then we have the thermal convection. And then we have the phase change materials, which are not insulating materials, but are contributing by thermal inertia, are contributing to the energy balance of a building. And with the PCMs, phase change materials, we are obtaining with a very small thickness, very good thermal energy storage because of the phase change, where we can use the quantity of heat, the energy of the phase change in solidification or in liquidification phase. Then we have the vacuum insulated panels that are very fragile but very effective. And we can use also transparent thermal insulation, which is combining convection, if we do not have a vacuum, transmission, but also radiation. And also we can expand this and complicate more with dynamic resistance components like ventilated space, ventilated windows, and so on. What we are doing with the materials, the most common case is using NETICS, external thermal insulation system, composite system. We have the insulation layer and several layers of protecting, of fixing, of ensuring the continuity. And the basic principles is to use plates, to use boards that are rigid, and even if they are from different materials, they can be put in place in a similar way. So we have the rock wool or stone wool boards, and EPS, XPS polystyrenes or foams boards. Each of them has advantages or disadvantages that are explained in here. What is very important with NETICS is that, first of all, we have to have an approval available for the whole system, not to use individual materials and to form the system on site. This is a usual practice, I think, but it's a wrong one, and it's affecting the quality of the building at the end of the building envelope. A common approval document means that we have a verification process that ends with a certification that proves that the components perfectly fit together. So this is very important when we are preparing the tender specification and the requirements for a building, to put this requirement to have certification for the whole system. And then, of course, to check on site if this is respected. There are many guides, most of them with photos. They are easy to be understood and applied. So it doesn't matter what technology and what supplier we are using. It's about respecting some simple things, some phases of preparation of the surface, bonding, anchoring, reinforcing, finishing, and using the right materials in order to reduce the, in our case, the He value, the punctual, the points, thermal bridges. So first of all, using an anchor with lower conductivity, which is plastic, or using more resistant nails, but not for the whole length of the anchor. To have blocking heads, for example, counterstruck into insulation materials to reduce the point He value, the thermal bridge. And of course, different technologies that should be used in order to increase the durability of the ethics once applied, and to reduce the thermal bridges. The plaster is very important, and we have to assess not only the durability, of course, the cost, but also the protection that is offered to the insulation layer, the moisture transfer among the different layers of the building envelope, and the behavior in reality of the whole system. And in terms of exposing the building envelope to the solar radiation, this is important in terms of protection, but also in terms of increasing the temperature, in terms of heating the surface. Because not only the color, but also the texture influence the solar absorptance of the surface. And of course, the higher temperature are on the surface of the building envelope, the higher the stress of the whole system, and insulation layer, the material is exposed. Just a few words about the ventilation facades. The ventilation facades are a structure of a building with an insulation layer, and after the insulation layer, we have a ventilation gap, a slightly ventilation layer that is ensuring the natural circulation of the air. In the summer, this is passively cooling the building envelope layer. It's better protecting the structure, and it's ensuring the liberation of the moisture that is passing through, the vapors that are passing through the structure, by letting in the sun, in the winter and in the summer, the drying out of the insulating layer. The thermal bridge is one of the most important, is the base bar. And this has to be continuous. It's not only about putting the components in the high quality way, it's putting the right materials. So the aluminum base bar, it's a crime to put it in a very insulated envelope. And the solution could be not only to put a plastic one, but not to put the aluminum base bar from the high conductance material, which is the structural materials, till the end of the ethics. Of course, the quality of the execution matters, and these are poor practice examples. This is not a flying facade technology or an innovative facade. It's just not respecting the technology for the ethics. And how difficult can it be? But unfortunately, the picture on the right is the usual practice that we can see on our sites. Of course, it's about respecting the technology when we are putting the dowels or the anchors, It's ensuring durability and minimizing the thermal breaches. And of course, the air protective layer that has to be continuous. I will stop here because I will complicate a bit from the slides that are coming now. Let's have a 10 minutes break. It's okay to recover at 10 past 12. I will take that as a yes. So see you at 10 past 12. Are we ready for the last part?
Yes, I think we can start.
Yep, let's go. So another important parameter that influences the thermal performance of a building material is the heat capacity, the volumetric heat capacity. And this is in relation with the thermal inertia, with the thermal capacity of internal walls and internal part of the building envelope that is contributing to the heat storage and as a consequence to the reduction of the energy consumption of buildings. What is missing here might be important is the wood, and this is important in the same context. It's important in the pitched roof in a occupied and heated last floor. That is offering delay the time of the maximum temperature outside in summer. It's delayed compared to the maximum load from the solar radiation. That is important in the designing of last floor, the upper floor with a pitch roof. But is thermal aspect of the building envelope sufficient? Combined heat, air, and moisture to building materials and building components, it's happening all the time. So we have to take care to prevent or to reduce moisture penetrating the construction element, and also to ensure sufficient drying capacity. This is the design in a moisture-safe and damage-free manner. And also, in the same time, it's important to design the right thermal performance, which is the U value, and also the C value in correlation with the linear thermal bridges, in order to reduce the energy demand and to increase the thermal comfort in the occupied space. And also it's a matter of internal surfaces and pollutants from construction materials that is affecting the indoor air quality. In terms of mold risk, the mold growth is directly linked with the indoor air humidity and surface temperature. It's about the state of the air. It's the Mollier diagram, the psychothermic diagram. So the lower the surface temperature is on the wall, the moister the surface of the building component will become. And mold spores are natural allergens. They need a specific environment, and in time, they will develop if the right measures are not taken, and they will affect the occupants. So how to avoid it? First of all, to increase the wall temperature. And we are doing this by increasing the thickness and the quality of the insulation layer, and to make it continuous. To promote low moisture condition. It's about the balance of the vapor emission inside. And this is from breathing, from washing, from cooking, from plants, drying laundry, and everything we are doing inside. So it's to control the moisture sources and to adapt the moisture sources to the ventilation and vice versa. To ensure a tightness of the building envelope, because if we can prevent the humid air to enter the building envelope, we solve part of the problem. Proper ventilation control, this is balancing moisture sources and building moistures with ventilation rate. and of course other things that are combination of the previous mentioned measures. So first of all, the benefits of vapor control is to prevent the humid air to escape into the external envelope. Then is to create outside a vapor open, a transpirable layer or phase to allow the vapor that enter the structure to get outside, to exit. It's reducing the risk of condensation and mold in the structure of the envelope, protecting the structural integrity, and reducing the formation of the sick buildings syndrome at the end. And this should be assessed from the design. There are two basic ways of analyzing this. First of all is the traditional method, the standardized methods, at least for the last 50 years, the Glaser method. It's a steady state method, very simple to apply. And it's very good to check if there will be or not condensation inside. It's not very good to quantify the accumulation of water. For this, we have dynamics methods, heat air moisture, HAM methods, which are compared to the laser method. These are dynamic methods. Are using these kind of methods, you can one can analyze in a long period of time if there is a risk of accumulation of water in the structure. And of course, we have to know the limitation of the tools. There are many tools that can be used. Most of them are commercial tools. The best one, I think, it's Woofy. It's a German software, I think. But it's very reliable, it's very detailed and quite easy to be used. It's a matter of balancing the air tightness, the heat transfer, and the vapor transfer in the structure of the building envelope. In order to see the cold spots, the critical details, we should use 2-dimensional simulations or even 3-dimensional simulations. The more we are going into 3D, the more complicated it gets. And as far as I know, there is no reliable tool to help in a push of a button to simulate in 3D the whole building. But of course, this can be done in a design best practice by using components of the building envelope and designing them in order to solve all the problems that we mentioned, and to avoid the consequences of the thermal breaches that once again are listed maybe in a more detailed way than in a slide that you could see earlier. So greater degree of the heat insulation of the buildings will lead to relative bigger importance of the thermal breach of the details of the joints in different materials or penetrations or of parts of the building envelope. So as a history written in one slide in Romania, in 1997, it was the first regulation on how to design a building envelope from the thermal point of view, how to calculate the thermal bridges, and we could see at that time some details that were 25 years ago like best practice. Then in 2010, it was a project building passive house. It was a very detailed research project in the courtyard of the Polytechnic University in Bucharest. And then in 2020, we designed the first mock-up and we built the first mock-ups in the Building Knowledge Hub in Romania in the Train to n-ZEB project. There is a huge difference between those details, and it's showing the evolution of how we treat thermal bridges in our buildings and in our designs. One other important aspect is reducing the heat transfer in the building envelope using cold surfaces or cold materials, for example, in cold roofs. Usually the construction materials have high solar absorptivity and facilitate high solar gains. So we are heating our external walls in summer and roofs. On the opposite side, the cold materials have high solar reflection, reduce solar gains, and have also high emissivity in order to release the heat, to radiate the heat to the environment. So the cool materials have high solar reflectance in order to maintain cool, not to overheat. And they emit the heat by infrared, the effect being the common lower surfaces temperatures. So it's less heat that penetrates into buildings and less heat transfer to the ambient air. But we should keep in mind that there is also higher level of radiation to the other buildings, so the effect is not so limited. Green roofs are influencing the building architecture, aesthetics, and are improving the air quality in the immediate environment of the building. They alleviate the urban heat island, maintaining the outdoor environment, the local environment with low temperatures. They are also improving building insulation and building solar control. But green roof performances are strongly influenced by the materials used, by the building characteristic, by the building use, climatic conditions, and of course by the quality of the workforce implementing those technologies. But I'm sure that you will find more in the other modules about the green roofs. So we speak a lot about the opaque part. The windows are a very important component of the building because we have the solar gains. So the G value, the solar transmittance is as much as important as the transmitter, the thermal transmittance value. G is from glazing, so UG is the transmittance of the glazing. And of course, the windows are one of the components that could allow an optimal energy balance, balancing the losses and gains in order to help the lower energy demand that we want to obtain. In a standardized way, the window transmittance, the window is a system, it has glazing, is the G, has frame, is the F, and the window, it's notated with W as a system. So we have the losses through the glazing, the losses through the frame, and the installing thermal bridge that are part of the calculation of the global thermal performance, thermal transmittance of a window. In terms of glazing, we have the single glaze, the double glaze, and some improved until the triple glazed technologies that we can find on the market. And depending on the technology, we have the different thermal performances, the G value, the resulting temperature at the inside, which is very important in order to compare with the risk of condensation. And of course, the If we add more glazing, we will reduce the solar gains by reducing the G value. But this is the key to the energy balance of a window, balancing heat loss and heat gains. And this is a basic requirement for the passive houses and for the nearly zero energy buildings. On the south, in winter, we might have higher gains than transmission that will compensate the other losses in the other components. And this is one of the key to obtain a very low energy demand. The window is a part of the thermal envelope. When designing new as well as retrofitting existing buildings, one needs to weight the solar gains and transmission losses of the windows, but also we should put a very high performance window in a very high performance wall, very good insulated wall, in the right manner, because this is depending on installation. It's not only about the product that is the window. The installation must address all the key issues from the watertight, airtight, structural sound, vapor smart, and not to affect the thermal performance of the window. What it matters the performance of the building envelope. And the difference could be quite high. Of course, the technology to install the window in line with the insulation might be very costly. But the costs might be recovered by the energy savings that are driven by the recommended installation. As we can see, maybe the Psi value is not telling very much, but the global U value of the window from a very good performant window, 0.8, we end up in a bad installation with 1.2 watt per square meters and Kelvin. And there are many technologies to install the window in line with the thermal insulation, external insulation of the wall. But first, let's see what is the impact on the overall heat losses of a facade. We have a very good window installed in a very well insulated wall. You can see from the transmittance, from the U values for window and for one-dimensional in the field. We have the design zone 2 in Romania, which is minus 15 degrees. A normal facade with a normal window. And we have 4 possibilities to install, 3 possibilities to install the windows in the resistance structure, let's say a brick wall, and the recommended installation in line with the insulation. And what is the difference? We can see the difference from, just a minute, from the isotherms, the lines or the curves of equal temperature. If they are aligned, everything is fine. If the distribution of temperature is disturbed, the more disturbed the isotherms are, the more the impact on thermal transmittance will be. And in terms of thermal transmittance, from 0.136, we got in the optimal installation technology at almost 0.15. And for the others, we have until 0.24, which is like, I don't know, 60–70% bad, worse than the one-dimension heat transmittance. So in terms of total losses over the facade, we could have almost 30% more with a bad installation. And it's a very simple question. Why pay so much on a very expensive window and install it in a bad position, having maybe the same effect than paying less on a maybe lower performance windows, but installed in the right way? And there are different technologies available with very varied guidelines in order to ensure minimum thermal breaching installation and an airtight windows installation. And of course, there are many examples of bad installation, maybe of bad products also. But basically bad installations in the usual practice that we faced day by day. And of course, we shouldn't support only airtightness of the building envelope. There are the two things that should work together, airtightness and ventilation. So, of course, build tight and ventilate right is the right way to go towards nearly zero energy buildings. The benefits of the airtightness we already listed. It's no draft, consequences is improved comfort, reducing the heat losses and consequently reducing the heating bills. Improved soundproofing, and this is very important because if we have a very good window and we install it in not in an airtight way, we will hear the sound of the street. And of course, circulating the right flow rates through the circulation, through the ventilation system is critical in terms of airtightness of the building envelope. The airtightness should be judged from the drivers, and the drivers are the wind, dynamic pressure difference, or the thermostat effect, the thermal pressure difference. If we want to build up a submarine, the scope, the purpose is to be waterproof. No, not to permit the water getting inside. It's the same thing with a building when we are thinking about airtightness. We need one concept, one continuous, uninterrupted airtight layer to enclose the thermal envelope. Why build airtight? Well, we already saw that. And how do we assess the airtightness performance? By doing the blower door test. During the blower door test, we can identify tracing leakages. We can repair if we can have access to the airtight layer. And this is done usually in a preliminary test, not only the final test. Because in the final test, as you can see on the right, we can identify a big leakage, air leakage, but we cannot do anything because it's behind the finishing. The quality control, it's very important. So why and who, of course, everybody should do something in their area, in the concept, in the design by speciality, and in the execution. Because we don't want to have this in reality. And in terms of quality control, every material and construction product has its own specific properties, and this should be taken into account in the design and also checked on the site. Materials and products incorporated into building must be compatible, and this is why we should check for the certification for systems, not only for individual materials. Each material and product should be used only for purpose prescribed by the producer, and not respecting these rules can result with the construction damage. Fire, penetrations affecting the health of the occupants. It's only about integrating planning, not to have two parts of the building or two different components that are not fitting well together, because we didn't thought of that, we didn't think of that, and we didn't execute it in the right way, and to have the workers and the execution personnel knowledgeable, skills, and responsible for the work that they are doing on site. In the quality check, we can use the infrared inspection using thermography to see the cold spots, to see the thermal bridges, to see the quality of the building, to see how the execution was done. And during the blower door test, if we have the conditions to use thermography, this is very useful to see also the air leakages where we have no access. As you could see in the previous picture in the summer, this is the cold spots in winter. It's the cold air that is cooling locally the surface that is seen as with a lower temperature, but by the infrared camera. It's also important to communicate the importance of air tightness in order to ensure the air tightness quality on site. So these are the examples from an Irish site. From the training course and an increasing quality of the execution from some bursting park, it was a project of renovating some social housing in Dublin to reach the passive house standard, the NFIT standard. These are the project, the architect, the designer, the passive house consultant, the general contractor, and the airtight applicators. And the guys from the Passive House Academy, the Passive House consultant, did a training with the workers on site, showing them and demonstrating and teaching them how to apply the air tightness technology. And at the end, the Passive House standard has been reached. Even the value for new buildings has been reached. And the workers understood very well what is the importance of what they did, of applying the airtight technology in the right way. And if you remember the first slide when we started with the n-ZEB definition, it was stated there that the details matter. And this is all about. The n-ZEB standard and the n-ZEB concept is not something new. The n-ZEB standard is only a higher level of performance that we had in the past. And the concept, it's better understanding the building physics. It's not something special. It's not an invention. It's not a discovery. Maybe for some of us, it's a discovery at one moment. But in fact, it's something that we should have known from school, from our education, from our experience. So basically, that was the concept. What I want to do in the next, let's say, 10 minutes is to show you some initiatives and actions that we were and are performing to enhance micro readiness for n-ZEB implementation beyond the official journal. So this is the Romania of years 2000. This is what we can still find, less and less, I admit, but 3 years ago we could find that as a common practice in our sites. And this is meaning that we are not n-ZEB. And there are many reasons for that. I've listed only some of them that could be the main barriers for accepting the n-ZEB and deep energy renovation practices. First of all, we have a comparably high investment cost. And of course, it's higher payback periods if you are speaking about deep energy renovation compared to usual practice renovation. It's about mobilizing the correct level of investment, and we are moving forward in that in our investment programs, is to solving the correct way the puzzle of n-ZEB by optimally integrate the existing technology that are suitable for n-ZEB for deep energy renovation. One of the biggest challenges, I think, is the quality and compliance and the skills gap. And we are doing a lot on training and raising awareness, but also on improving the technical regulation for the quality and compliance. And of course, it's the market that needs business models, reliable and economically viable, in order to accept this high level of standard of performance. And it's about all the guys with neutral faces to transform them in happy faces on the right. And of course, if we take step by step the barriers, first of all is the cost. If we are speaking about initial cost, of course, we will say, no, you cannot do n-ZEB because it's so expensive. But in some cases could be more expensive if you are doing in a cheap way, because you will pay a lot in the operational phase. In the 30 years that you should take into account when you're assessing the feasibility of one technology or another. It's about compliance frameworks in order to have a skilled workforce, but also to have in reality what you have in the paper, in the technical design documentation or in the energy performance of building. And these are two initiatives that are closed for some years, the QualiCheck and the Republic ZEB. There were Intelligent Energy Europe financed projects. It's about taking care of the object of investment when you are dealing with public money, more than you are dealing of the investment itself. Because most of the people in the public administration or agencies that are implementing public funds, they are taking a lot of attention, they are paying a lot of attention on how they spend the money in terms of respecting the rules, not attracting the court of auditors, or whatever control. But less attention is paid to the object of investment itself, which is the building, the quality of the building and the performance of the building. So the tender specification is very important, and the verifications that are put for each performances in the technical specification, in the tender specification, are equally important. These are the building knowledge hubs that we build up in the Train to n-ZEB project based on the experience from Ireland. The passive house consultant that you saw in the pictures is Thomas O'Leary, together with Ad McCormack, that you can see in some of the pictures here, where our consultants on how to build training, practical training facilities. I think in Ukraine, you have the one on the top right. So we did that in the Czech Republic, in Bulgaria, in Romania, Ukraine, and Turkey. And the basic concept of the Building Knowledge Hub is to have a hub developed based on the terms of reference that are still available if you have the curiosity on the train2nzeb.com website, to have services on demonstrating the technology, on having consultancy and research and development actions on n-ZEB, to theoretically and practically train on-site workers, specialists and designers, but also decision makers. You are, most of you here, decision makers, in order to solve the puzzle of n-ZEB to ensure the technology integration. So it's also about technology, and we discussed a lot today about technology, but it's about people. It's about people discovering these technologies, understanding the technology, and being prepared how to take care in the design phase, in the execution phase, and in the operational phase, those technologies and those principles, those pillars that are forming either the passive house concept or the n-ZEB concept, as you have seen. And in the Train to n-ZEB project, we translated, we adapted, and we implemented the two passive house courses, one for the tradesperson, for the execution workforce, and the other one for the designer or consultant, certified specialist for passive house. And we have more than 120 certified tradespersons and more than 130 certified designers and consultants in Romania. And we are continuing that in the n-ZEB Ready project. The n-ZEB Ready project is a project that it's in the last year of implementation. It's under Horizon 2020 program, and we started from analyzing in 5 countries. We have Poland, Portugal, Croatia, Bulgaria, and Romania. We assessed the level of readiness for n-ZEB implementation, and we found out that we have much to do on 3 pillars, starting from 3 simple questions. Why n-ZEB? And we target the low awareness of the benefits of n-ZEB. Who can provide n-ZEB? And we are developing and implementing, testing, piloting now 13 courses for short duration specialization courses for n-ZEB. And how to reach n-ZEB? We are putting up together some guidelines and supporting instruments for implementing the n-ZEB concept and start in the 5 countries. So these are the 13 courses. We are now piloting each of them once or twice, depending on the country. There is a large target group definition with short courses, 2 days, with a lot of practical content. Another project that has ended but is continuing is the n-ZEB Roadshow. This was the concept of putting the building knowledge hubs on wheels and go to the caravan, to the roadshow in other cities, in our countries. And we did that in Italy, in Bulgaria, Croatia, Greece, and Romania, with a national scale marketing and communication campaign. So we did some noise, basically. We tried to personally engage all the stakeholders in 2 to 5 or even to 6 days. It was called the n-ZEB Weeks, with various demonstrations, games, and conferences, workshops, training sessions, using mock-ups. So we build up mobile units, mobile mock-ups to go from city to city. Free consultations on design documentations to architects or to beneficiaries, panels of discussions, debates, site visits to buildings built at n-ZEB level. Gamification was part of the concept. Networking through experience change between professionals and learning from professionals to other professionals. In Romania, this is what I want to briefly show you. We planned 4 cities, but we did 5 at the end. We started in the pandemic window in Bucharest in July 2 years ago with 6 days. Then we had the what we call the chariot, is the mobile unit ready And we started last year in May to Brașov in the center of the country, then in the northeast in Iași, then in Transylvania, in Cluj-Napoca in autumn. And this year we did an extra town, which was Timișoara in the west. And yeah, in Timișoara I have many pictures. I will get quickly through them because now we did last week the 6th edition. I don't have any pictures. It was an intense one. In this big event in the 5 cities, we demonstrated that we can do after the project stops. And in Timișoara in May this year, Timișoara is now this year the cultural capital, European capital of culture. So we went there to do the culture of n-ZEB. And it was about exhibition. We had 50 partners, 50 companies exposing the technology. You can touch the technology. You could speak with the experts about the specific technology in all the principles that I presented today. We had games. We had visits on site. We had children, the future of the construction sector, with children games, with adult games, with a cartoon book, with n-ZEB. n-ZEB is the dog teaching kids from 4 to 7 years old what are the principles of n-Zero energy building, with demonstrations. And this is our chariot. We demonstrate how you can do the blower door test. And we put a lot of smoke inside. And of course, I think it's the best demonstration to see if there is smoke, this is not airtight, and then you will have heat losses. And this was done live. And from Brașov to Timișoara, we increased our number. It's a community that is increasing. And this is the final picture in all our events. It was about 4 days in all towns. And we form a concept of event, we form a recipe. And last week, we implemented again in Bucharest. It was even bigger. We had more than 80 partners exposing with a very, very large exhibition, with a stage where we had debates, panel presentations of technology, of solutions, workshops. In a, I would say, not a conference, not an exhibition, but overall a nearly zero energy building festival. Because it's about technology, but it's also about people. It's about a community that we all should form, we should develop, and we should maintain in time, because the construction sector, it's an organic one, because there are many people involved. So if we don't prepare our people, we will not have a high quality of buildings that we are designing and implementing. And that's all. Thank you very much. I think we have like 5 minutes or more if you need, in order to discuss about what we have heard today. So thank you very much for your patience. Are you still there? I have some questions. One I can understand. Is there any database with buildings certified in Bucharest? First of all, even if there is an obligation, in Romania, we do not have a functional database with the EPCs, with energy performance certificates. So we cannot say anything about Bucharest or about the country in terms of certified energy performance. We have a an investment in the resilience and recovery plan that is very much delayed. That is called the Digital Building Registry. That is under preparation now. So in the future, we might have a functional database with energy performance. And if we can look on energy performance of buildings, we can see if there is a nearly zero energy building or not. But there are many, I would say, databases, many inventories. Bucharest, maybe you know or not, in Bucharest we have 6 districts and we have 1 capital. So we have 7 local authorities. The local authorities is a district one, but we have an umbrella, which is the capital. So basically the buildings are under the responsibility of the districts, of the sectors. And some of the sectors, some of the districts had some inventories of basic energy features of the buildings. So this is more or less available in some sectors, but only if it's about the renovation of the building stock, and mainly on the block of flats, on the condominiums, not on individual houses or single family houses. But on the other side, you have the international database of passive houses that is available from the Passive House website. There you can filter on Romania and you can find the buildings that were certified or that are recertified as passive houses, classic, plus or premium, or low energy. So you can explore that database of buildings. And what I can say is that from 10 years, in the last 10 years, the community of professionals, as you can see, we have more than 250 persons certified for passive house. But also the buildings. There are many buildings that are intended to be certified at passive house standard. So I hope this answered the question. For Evgen, I think I know a little the letters, but if there is a question, I will ask the interpreters to translate them. Evgen Yurchenko, I think.
That's not a question, that's words. Yeah, our participant says that information you presented is very useful, and this information is not very easy for understanding, but the way you presented was I see one more question, maybe. Thank you a lot for the presentation. Do you have plans to organize specialized training on Windows installation?
I cannot hear you very well.
Materials
maybe,
for... Oh, sorry.
Maybe if you keep the same distance from the microphone, it will be better.
Maybe now it will be better.
Yeah, it is.
So the question is, thank you a lot for the presentation. Do you have plans to organize some special trainings for Windows installation or materials for insulation or passive house, etc.?
Yes, we have a lot of plans and we are very busy with the trainings. First of all, in Romania, we have to pilot 24 sessions of 2 days training in the n-ZEB Ready project on 12 of the 13 programs that I present listed in the table in one slide. We started with blower door testing, and it was the first blower door testing training in Romania. We will do another one next week. We did a pilot on ventilation system and air tightness. And next week we will have on thermal bridge calculation. In 2 weeks, we are planning thermal bridge evaluation with infrared inspection. And until the end of the year, we have another one planned, n-ZEB for designers on civil engineering. Unfortunately for you, these trainings are physical, are in Bucharest, and are in Romanian language. So if you can understand Romanian language and you can come to Bucharest, you're more than welcome. On the n-ZEB-ready.eu website, you will find all the learning outcomes as definition of the 13 training courses that we developed in the project. And I don't know if you're closer as language or geography to Bulgaria or to Poland, you can go there and then watch them if they announce courses on that. I don't know about any training course that we in our cluster or our institute are organizing in English language. Even this course I have to dedicate like 2 or 3 days to prepare it because I didn't have it prepared. So we do not plan to have English or Ukrainian language courses. But I would be very curious to find out from you if there are some training courses organized by the Building Knowledge Hub in Ukraine, in Kiev. If you have heard something from the last years.
I can add those that you said, Horia. So the purpose of that series of courses in the frames of our project is only the introduction into the topic of green building, and this course about near zero energy buildings is a part of 6 courses which is provided by Smart FOEU project. So, but in case if you will be interested to learn more about different topics, for example, this training, we will discuss it inside of the project, and maybe we will organize some additional courses for the needs of some additional understanding.
Yeah, of course, you answered the question in the perspective of the Smarter for You and the Green Building Professional series of training courses, in which I'm involved only for this module. But my question was regarding the building knowledge hub that was developed in the Train to n-ZEB, and the partner in the Train to n-ZEB project at that time was because I found it, all Ukrainian charitable organization called Municipal Development Institute, MDI. I don't know if they continue the trainings or together with the University of Architecture and Civil Engineering in Kiev, if they continue the use of the practical training facility and the deployment of the trainings that were organized at that time.
No, I haven't heard about that possibility. So anyway, we will discover this possibility. We'll try to contact with that people and understand if they are actively operating or not.
Good. Well, thank you very much for your patience.
Thank you.
Preoccupation.
Maybe some more questions from our participants. we are close to the end of today's course, and now if you have some additional question, it's the best time to ask. I cannot see any new questions in the chat, so I haven't seen any raised hands. So that's makes me understand that no question at that stage, and I would like to say words of thanks to our trainer, to Horia, for that interesting, very practical presentation and information about near zero energy buildings. Thank you for your work. Thank you for your time you spent with us these 3 hours. Thanks to all our participants, and before we will end this course, I would like to invite you to participate in our last training scheduled for this year. It will be December 8th, and we will talk about green design principles. So it will be the last course for this year, and in 2024 we will have the last one about financial aspects of green buildings, and after that we will provide you with certificates that you participated in our trainings for green building. So see you on the next courses. Thank you, Horia, for your nice presentation. We will provide information about today's training together with press release and the presentations on the website of Smarter for EU project and on the website of association. So thank you, Horia, thank you all the participants, and wish you all the best.
Thank you. It's tak ďakujem.
Yes, ďakujem.
Okay.
Ďakujemo.
Ďakujem. Okay.
I will stop recording.